Hello everyone. In this video, I'll be presenting my study on insurance claim prediction. This presentation will first explain the business problem, followed by the dataset and some exploratory data analysis, and then diving into the technical models. The problem I'm trying to solve first to develop predictive models to predict customer claims for a car insurance company, and to deliver data-driven insights to support the business to make decisions, as well as comparing the predictive power for two deep learning models with a baseline model. Now, this project is based on a car insurance claim dataset from a motor insurance company, and the training dataset has about 8,000 observations and 25 variables. There's also an evaluation dataset where we fit the best model to make the final predictions. The target variable for this dataset is named as target flag, which is a binary variable that indicates whether a claim has made. The first 5 lines of the datasets are printed on the slides. Next, I'm not going to get into too much details here for the EDA, but the most important thing I want to mention is that the dataset is imbalanced. The training dataset has a claim rate of around 26.38%, and to address this problem of having an imbalanced dataset, a 1-to-3 class weight ratio is applied for all the models trained later on, and I will explain the model training in the next few slides with more details. Before we train the model, the dataset is split into a training set and a test set with an 80-to-20 ratio. And for training the deep learning models, all the categorical variables are encoded using the ordinary encoder to convert them into numerics. And for the numerical variables, they are standardized such that they lie within the range between 0 and 1. And moving on to the models. 3 models are fitted in this project. For a starting point, logistic regression is chosen to be the baseline model, where we compare this with the deep learning methods. The first deep learning model is a deep neural network with 3 hidden layers, and with 64, 32, and 16 neurons respectively. Lin-Hiralu and sigmoid functions are chosen to be the activation function for the hidden layers and the output layer respectively. And the training set is further split into a new training set and a validation set. And the purpose of this is to fit the neural network on the training set and to examine the loss function and its out-of-sample performance on the validation set. Furthermore, a 20% dropout is applied after each hidden layer to avoid overfitting, and the number of epochs is said to be 500 with an early stopping. And the last model is the same neural network as the one we just talked about, but with entity embeddings. Embedding layers are applied to each categorical variables with more than 2 levels. Using embedding layers, it can really help to reduce dimensions and to avoid an excessive number of network parameters. Lastly, the preliminary results for each models are presented in this table. And from this table, we can conclude that there isn't a significant improvement in the deep neural network without embeddings compared to the baseline model. However, by applying embedding layers, we can see that the network improves the baseline model results evaluated on the test dataset significantly for all 3 metrics. Thus, we would prefer embedding layers over ordinary encoding for categorical variables. However, it's also important to point out that this doesn't mean neural network is always a better choice than logistic regression, because we haven't been investing sufficient effort in finding the optimal logistic regression model. And that concludes my presentation today. Thanks for listening.